Hello grade 9s, welcome to week 5 lesson 1. This week we're going to use relationship among chords, tangents, and radii in a circle when solving problems. So basically we're looking at relationship of lines in the circle. Last week we looked at angles in the circle. This week we're looking at lines in the circle and the different properties that are associated with it. You're going to be using what you know about angles in the circle and lines in the circle to solve problems in circle geometry. For this week's resources, you're going to use this video to complete the examples in this lesson. You can also use your workbooks 8.1 and 8.2 as a practice of these concepts before you try task number 1. For task number 1 this week, I want you to complete it, take a picture, and submit it on D2L. Okay, so let's start with our properties of lines in the circle. We're going to start with the first one. It says perpendicular bisector of a chord, a line that passes through the center of a circle and is perpendicular to a chord bisects the chord. Okay, remember, just to recap our vocab here, perpendicular means it forms a 90 degrees angle. Okay, bisects means it cuts in half. Okay, so this is basically saying that if you have a chord and you have a line that's extending from the center of the circle, it's going to form a 90 degrees angle, and it's also going to cut the chord in half. And each halves are going to be equal. So this side, if this is 5 centimeters, this is also going to be 5 centimeters. If this is 1 meter, this is also 1 meter. Okay, so again, a line that passes through the center of the circle and is perpendicular, forming a 90 degrees angles to the chord, bisects the chord, cuts the chord in half. Okay, so let's actually use that property to solve a question down here. Okay, I added a picture over here for us to remember what this property is. Looking at the question, it says radius CD bisects the chord AB. That's why these lines are here, saying that this side and this side are equal. Chord AB measures 8 centimeters. So let's actually circle that information. Chord AB measures 8 centimeters. And the radius of the circle is 5 centimeters. What is the length of the segment CE? So it's asking us to find the length of CE, which is right here. Okay. What we already know is that looking at this example or this property, because this is the radius that bisects the chord, it's always going to form a 90 degree angle here. Okay. Then we can almost look at this as its own triangle. We can draw it out here, where we have C, E, and A. Okay, and let's use the information to fill out what we know already. If chord AB measures 8 centimeters, if this whole thing is 8, if you cut it in half, A to E is going to be 4 centimeters. This side is going to be 4 centimeters. This side is going to be 4 centimeters, totaling to a sum of 8. And then it also says that the radius of the circle is 5 centimeters. The radius is half the circle, so it is C to D, but it's also C to A. Those are both radiuses of circles. So our C to A is our radius, meaning that this is 5 centimeters. And our question asks, what is the length of the line segment CE? Although we know that CED, so this whole thing adds up to 5, we don't know what CE is, okay? But we can find that out because we have a right triangle right here with one unknown side. So we're going to use Pythagorean theorem, okay? Which is a squared plus b squared is equal to c squared, okay? We just fill this in. Let's say this is our side A, B, and C. Okay, A is 4, so 4 squared plus B is what we don't know, so X. C we know is 5, so we write 5 squared, and we just solve for X. Take away 16. X squared is equal to 9, so X is equal to 3. So this is telling us, X is equal to 3 is telling us that this section over here, CE, is 3 centimeters. And that's what the question was asking us. What is the length of the line segment CE? So we just write that line CE is equal to 3 centimeters, and that is our final answer. And here We just use the property of perpendicular bisector of a chord. Okay, so let's go to our second theorem, second property. It says tangent to a circle. This property says a tangent to a circle is perpendicular to the radius at the point of tangency. So it's basically saying this line, the tangent line, okay, this is the tangent because it just touches the circle at one point, that point of tangency, is always going to form a 90 degrees angle with the radius of the circle. So this is the radius of the circle and this is the tangent line, so it's always going to form a 90 degrees angle. Let's say we have another tangent line here. Okay, so let's say this is a point of tangency and this is our tangent line. If you draw a radius right here, this is also going to form a 90 degrees angle. Okay, so the radius of a circle and a tangent line to the circle always forms a 90 degrees angle. Okay, now knowing this, let's try a question on this side. Okay, again we have the diagram right here to help us remember the property. Let's look at our first question. What is the measure of BDC? BDC. Do you see how we have the angle BDC right here? Okay. Do you see how line AB is tangent to the circle and CD is the radius, meaning that this is going to form a 90 degree angle. So our answer to the first one is angle BDC is equal to 90 degrees angle. We can say that this is 90 degrees according to our property right here. Okay. Next one, it says, what is the measure of DCE? So this big angle right here. Okay. We can't really tell. This one, that doesn't involve a tangent line, so we're not going to use this property, but we're going to use everything else we know about circles, angles, and triangles. Okay. What we know already is that this angle right here, this angle that's formed from EB line, this is a straight line, so this whole thing must be 180 degrees. Okay, but it's asking us only for the part of that. So let's see if we can find out what this is to help us find out this angle. Okay, looking at this triangle right here, we know that all angles in a triangle equal to 180. Okay, so for that one we say all angles in a triangle have to add up to 180 degrees. We already know that two of the angles, this one is 90, this one is 50. Okay, we know two of the three angles. So from 180, we take away 90, take away 50, and this gives us 180 minus 90 is 90, minus 50 is 40. 40 is remaining. So that is telling us that this little angle right here must be 40 degrees to make all three angles add up to 180 over here. Okay. All right, this is a key piece of information to help us find this angle right here, because this whole thing must be 180 since it's a straight line. Okay, then that means if this little part is 40, this part right here must be 140 degrees. Okay, so for this one, angle DCE is equal to 140 degrees. Okay, and now the next question is asking now for the measure of DEC. DEC is the angle right here. DEC is the angle right there. Okay, to find that one now, let's see what else we can find. This is part of this triangle right here. It's also part of this big triangle right here. This big triangle, we know one angle, but part of the second angle, so we can't really use that information. But if you look at this triangle right here, what kind of triangle does it form? It forms an isosceles triangle because two of the sides are equal, because they're both the radii of your circle. This is the radius, this is the radius. So this side and this side must be equal. So I will just indicate that right here. What else do we know about isosceles triangles? They not only have two equal sides, but these two angles are going to be the same. Okay, so that means, looking at this, all angles in the triangle have to be 180 degrees. We take away the 140, and we are left with 40 degrees. 40 degrees have to make up these two angles right here, one over here and one over here, because this is 140 plus this has to give us 180. We have 40 degrees remaining to use. These two must be equal. So we go 40 degrees divided by 2. That gives us 20 degrees. Okay, so that means angle at DEC is equal to 20 degrees. Angle at CDE is also 20 degrees because it's an isosceles triangle. Okay, notice how for this question, we started with using the property of tangent to a circle and identified a 90-degree angle here. But rest of the problem, we used what we know about triangles, that all angles in a triangle have to equal to 180 degrees. We also used a straight line. We know that a straight line has to be 180 degrees. We used that information. And for the last part, we also used what we know about isosceles triangles, how they have two equal sides and two equal angles, okay? So this is what I mean by you need to use everything you know about circles, triangles, and angles to solve questions in circle geometry. Okay, let's look at our last property. Last one is the tangent chord relationship. It's very similar to the one that we just did, okay? So this one's basically saying a chord drawn perpendicular to a tangent at the point of tangency contains the center of the circle and is a diameter. So if it's saying that if this line forms a 90 degrees angle with the tangent, then this line must be the diameter of the circle, or part of that line is also the radius of the circle. Okay, so this one is saying if it forms a 90 degrees, this must be the radius. This is saying if this line goes through the center, it will form a 90 degrees. Okay, a chord drawn perpendicular to a tangent at the point of tangency contains the center of the circle. Okay, so one more time, a chord drawn perpendicular. So if a chord forms a 90 degrees angle with the tangent, the line must be the diameter, or part of that line is also the radius. Okay, so remembering that, let's look at our last example. Okay, so this one, it says, what is the length of the diameter? BD, diameter BD right here. Okay, in this case, we kind of have to extend our tangent line here for it to be obvious, okay? Do you see how this line, we can extend it out? It becomes a tangent to the circle, and B is our point of tangency. According to our property here, the line, the diameter of the circle, a chord that passes through the center of the circle, and the tangent line will form a 90-degree angle. So let's indicate that right here, that this is a 90-degree angle. Okay? All right, with that information, what is the length of the diameter BD? We can find this easily because it's now a right angle triangle and we can use a Pythagorean theorem. Okay, so we're going to use a squared plus b squared is equal to c squared. We'll say 7, this is our a. 7 squared plus b squared, well, that's what we don't know, so x is equal to 25 squared. X squared is equal to 25 squared minus 7 squared. Okay. X squared is equal to 625 minus 49. This is equal to, grab a calculator, 625 minus 49 gives us 576. X is equal to square root of 576, which is 24. Okay, so the diameter of the circle, so diameter BD is going to be 24 millimeters. Okay, watch out for the units here. Okay, now let's look at the next part. It says, what is the length of the chord BE? Notice how BE, it's indicated that BE is the same thing as CE is the same thing as BC. These little lines mean that these three lengths are the same. These three sides are the same. So this, we can already tell, is an equilateral triangle. Okay? We can't really tell what this is, but we know that BC is the radius of the circle, and we just said that the diameter is 24. That means our radius is 12 millimeters. So that means this is 12, this is 12, and this is 12. So the length of chord BE is equal to 12 millimeters. Okay. And now it asks, what is the measure of the inscribed angle BED? BED, right here. Okay, this goes back to last week's lesson, remember? If an angle is formed, an inscribed angle is formed from chord BD, which is the diameter, this is 180 degrees. The inscribed angle is half of that, so BED is going to form a 90 degrees angle. Okay, so angle BED, we say, is 90 degrees angle. Okay, last one. What is the length of the chord DE? Okay, what is the length of the chord DE? Chord DE is right here. DE. And it's asking us to get the length of this. Again then, do you see how we have a right triangle here? And that's what we're going to use to solve for DE. So because we have a right triangle here, we know that this side, the A side, is 12. We don't know the B side. We know the C side because C is our diameter, and we just said that the diameter of BD is 24 millimeters. Okay, so to get that, we're going to use A squared plus B squared is equal to C squared again. Again, our A is 12. 12 squared. B is what we don't know because that's what we're asked to find. X squared. C is our hypotenuse and that is our diameter. And we said our diameter was 24. So we go 24 squared. Okay. I'm just going to move this over here to solve so that we have more room. We have 144 plus x squared is equal to, what does 24 squared give us? It gives us 576. Take away 144 on both sides. X squared is equal to 432. Okay, and last thing we need to do is square root both sides. X is equal to 20.8, okay, to the nearest tenth. Okay, so our final answer for this one is chord DE is equal to 20.8 millimeters. Again, watch out for units because it's not always going to be centimeters, okay? All right, so for this one, we use this theorem to help us identify the 90-degree angle here, and then we use a lot of Pythagorean theorem, and we also used what we know about equilateral triangles having the same sides. Okay, so if you are struggling with the Pythagorean theorem, I will post the link to a practice. I want you to practice that before trying these questions, okay? But again, it's like a big puzzle. You're using everything you know about circles, triangles, lines in a circle, angles in a circle to solve problems, okay?